So now we are starting with the last portion of this chapter. So still in nervous system, chapter 10, starting with that. Okay, so we have just finished with talking about how a nerve impulse actually is conducted through any part of the nerve cell, but really I was drawing the axon, which you see here in this picture, the axon. But again, it's going to be any part of it. So it could be the dendrite, the cell body, or whatever. But we always use the axon. It's just the longest part, and that's where the majority of the movement of that impulse is actually going to go on. Now, remember that as an impulse occurs, it's actually occurring through that neuron. So what we're talking about is like the gray that, or light blue or whatever, purplish blue, that you see of this axon. So it's going to be occurring here, and I've got the sodium here and the potassium here, and the sodium flows in and the potassium flows out, and all of that's going on. That really only occurs in that neuron. If you see right here, around the neuron, I have that myelin. And myelin, as I told you earlier, is something, it's like a fatty type of substance, but it speeds up our impulse along that. And the way it does that is it actually allows this impulse, all of this trading of the sodium and potassium that's occurring all the way down the neuron, can actually skip sections. So it's really only occurring in the areas that's exposed right here. And then it skips completely past where that myelin is. And then again, only has to do that sodium potassium thing right there. And then it skips again and it goes right there. It's kind of like, like reading a book. You can read from cover to cover on the whole book, or you can read the intro of each chapter. And if you still got the same information out, which you wouldn't, but if you did, it would be much faster to read the chapters, right? Or, the intro to the chapters instead of the entire chapters, because you're skipping entire sections in there. And that's really what the myelin allows the impulse to do. Skip really long sections and just jump from section to section. Those little sections right there that are exposed where this is actually occurring, so this little sodium potassium thing is occurring, these are called the nodes over there, nodes of Ranvier. Okay, so it's nodes of Ranvier are those little sections in there. So it skips from one node to another node to another node and really just bypasses that whole section in there. This process of jumping past that myelin-coated area, this is called saltatory conduction, and that just means that the ability to send a message is much faster. I do have a link in here for saltatory conduction, so if you want to click on it, it depends. Sometimes it's a good link, sometimes it's a bad link. It's really just a link to like a little YouTube video, but I'll find one and put it in D2L for you, whether this one works or not. Every time I find a good video, they end up taking it down for me, and then it's not good the next class period. All right. Now, when we're looking at this, we have something also that I referred to earlier sort of in passing, and I talked about the all or none response. So like flushing the toilet, you can push down on the handle of the toilet, but only to when you get to that certain point. Once you hit that certain point, it's going to flush or it's not going to flush. I can make the water start going out of the toilet as I open that little rubber stopper thing that's allowing this to happen, but it really doesn't flush until you hit that one point. That point is what we call threshold. And once you've reached threshold, misspelled that. Once you've reached threshold, the two H's and there isn't. Once you reach threshold, then the response that's elicited, in other words, the impulse that's going to go, it's all or none. So it either hits threshold, and so it sends that response, that's all. It never meets threshold, so then it's none, and there's no response that's sent, okay? It doesn't go at a greater speed. It doesn't go at a greater force. It's either there or it's not there. If I want more things to happen, then I'm going to have to include more neurons basically in there. So all the impulses that are sent along that axon are going to be exactly the same every time. But if I want to, like send those impulses to a muscle and make the muscle do more work, then I'm going to have to send down several different neurons to get those more muscle fibers involved. But each impulse by itself is the same. Okay, now once you've sent an impulse, and I showed you that old graph where it went here was the impulse, and then we hyperpolarized for a second, and then we came back to resting potential. There is a time period where you cannot just immediately go to another impulse. Okay, so I have to have this sort of rest period. This is what we call a refractory period. A refractory period is that period when it doesn't matter Okay. If I reach threshold or not, if it's too soon, I'm not going to send another action potential. Remember, action potential and impulse are the same thing. So if I don't make it through that refractory period, it doesn't matter what happens. It's not going to happen. Absolute means there's no way to make it work. There are some cases where you have something called a relative refractory period. So I might be able to get a stronger threshold or a little more information coming through to the neuron, right? That can actually start another action potential without a full sort of rest period in there. The thing I like to think about when you do this is kind of works this way, but thinking about smells, when you smell something, you send an impulse, so an action potential to the brain. The brain recognizes that smell, and then you've got the memory, and so you realize what it is, and you say, okay, that's good smell, bad smell, whatever it is. It's perfume, it's vegetables, whatever is going on in there. But there are some smells that are lingering, and after a very short period of time, we stop just smelling them. If you've ever noticed that, you stop smelling your perfume after you put it on, or you stop smelling, the Christmas tree. If you've got a live Christmas tree, when you walk in the door, you smell it for the first time, but when you've been sitting around the room, you really don't pay attention to it. There's a couple things going on in there. Part of that is your brain just ignoring stimulus that it doesn't need to pay attention to. But another one is this threshold thing. So like going back to the perfume, I spray the perfume on, I stop smelling the perfume. The only way I can smell it again is if I refresh. So I spray another round of that perfume on me, give myself another whiff and hit that threshold again, and then I can smell it. Somebody else comes into the room and they're smelling a double whiff. You just got double sprayed, and they're like, go easy on that. But you didn't smell it. You thought it was all gone, but it was just there. It's just that you weren't able to send another impulse to the brain saying that was there. Okay, that would be more like a relative. All right, so when we look at the impulse or the action potential conduction, this is a summary of all of those steps that we talked about. So when you're trying to go back through, and I would say draw it out and look at the impulse and go back through, where's my sodium, where's my potassium, resting potential, action potential, polarized, depolarized, all of that kind of stuff. Go back through, and here's the steps that you have to go through in that. Remember, sodium is first. Sodium acts faster. So sodium flows in first. Potassium is a little bit, those channels are a little bit slower in action, so they lag behind. And we really want that to happen because remember, sodium open, and then you hit that 30 millivolts difference, and then the sodium channels close and the potassium open so that I can repolarize. We don't want both opening at the same time. We want this ability to repolarize. So you have to have that potassium channel to lag behind a little bit. So sodium channels are faster, potassium channels a little slower. That allows for that impulse to send a wave down that axon or that neuron. This link is in D2L for you, and that goes through all the little pictures I drew for you. This is an animation of that. You can see the positive and the negative. So here's the sodium, here's the potassium, and it's going to show you that movement of stuff, and it has little channels that open and everything in there. So it's going to show you all that stuff through there. All right, things that affect our impulse conduction. Obviously, sodium, you got to have enough sodium if you're going to have it flow through. Potassium, we talked about, that's another one that you're going to have too. But we also have these other ions to consider. So I'll come back to especially that one in a second. So calcium. Remember, calcium is at the end of our neurons. So here's my electrical impulse with sodium and potassium going in and out of the cell down here. And once it gets down to that end of the axon, what's called the axon terminal, that electrical signal stimulates calcium to open, and the calcium flows in, and that's going to stimulate the neurotransmitters like acetylcholine to jump into the synapse, right? Another thing, well, we talked about it with muscles. Another thing calcium does is remove the troponin, or bind to the troponin to remove the tropomyosin out of the way. So it has an important function there. It also has a function in closing our sodium channels. So when we're looking at the impulse, and I've got sodium flowing, that's the wrong way. I was thinking the other direction there for some reason because I put it sideways, I guess. You've got the sodium flowing in, right? First thing, I'm going to have to close those channels so that the potassium then can flow out. calcium is responsible for signifying, hey, it's time to close that sodium channel. So what happens if I don't have enough calcium? I'm low in calcium, I'm not going to have the signal that says close these channels, block any more flow of sodium in, so sodium's going to keep flowing in. Your channels stay open. That means you continue to send this contraction or send this impulse to like muscle, right? Muscle fibers, continuous over and over and over again. And the muscles keep getting the signal that says from the neuron that says, go, 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 right? So it leads to a continuous contraction. That's something we call tetany. Tetany is a continuous contraction that doesn't stop, and you can't stop it really easily. Potassium. Potassium ions are needed to flow out, right? So that I can repolarize my membrane. Well, if I have too much potassium, let's go ahead and erase some of this. I'm not even, I need it to flow out of the membrane, but let's look at the very beginning here. So here's my neuron, right? When I set up at the beginning, my resting potential, right? Resting potential here. And I've got all my sodium here, and I have fewer potassium on the inside. What happens if I have more potassium, right? What happened to my charge right there? Now I don't have that negative 70 millivolts difference. Actually, in my drawing, they're equal. It's a zero difference, right? So now instead of, in that little graph I was showing you, where we got this, instead of starting out at negative 70 down here, right, and then hitting threshold at negative 55, I'm already starting, in my picture, I'm starting way up here at 0. But if we're just even a little bit, we're already starting at a higher level. We're starting closer to threshold, right? So that means you are much more likely to hit threshold when maybe you shouldn't. Maybe it shouldn't be sending a signal. It's got a little bit of impulse, but we got to make it die out and not carry on. But since I have such a little space to travel here to get to negative 55, those fibers are really close to threshold all the time. They're highly excitable. They're going to be sending messages like all the time, rapid fire. And that leads to things like convulsions, because you're sending a message because you're right there by it, instead of maybe starting some of it and then not finishing, and stuff, so that you can regulate what's actually being sent. You're right there, right by where you need to send it. So too much potassium can be a bad thing. We always want the right amount of something. We don't want too little. We don't want too much. So you don't want to increase the amount of potassium either. What happens if I decrease the amount of potassium? So let's draw that in. So here's my sodium. I'm at resting potential, right? I've got all of the sodium here. And remember, it was a 3,2. So I'm going to draw, this is 3,2, right? 3 sodium out to 2 potassium in. Set it. What happens if I have too little? So now I don't have that one there. So I'm supposed to start at negative 70, but now I have increased my negativity. So now I'm starting out at maybe negative 80 millivolts. That's another problem. So here's my graph, right? Here's my graph again. I'm supposed to be starting at negative 70 because here's threshold at negative 55. Well, if I start out lower down here at negative 80, negative 90, I'm going to have travel more. I'm going to have more sodium flow in than would normally flow in to even reach threshold, and I may never get there. So what you end up with is the right amount of sodium flowing in, and I just get to this point and I never get to threshold. So what happens to the impulse? Nothing. So you end up with no impulse, no stimulation to the muscles. They're paralyzed because they're not getting the information from that neuron. So again, the right amount is good. Too little, too much potassium is going to affect what's going on with your difference in charge there, and that's going to cause a problem with whether you're going to send an impulse or whether you're going to send too many impulses. We can, however, kind of capitalize on this. So we can use this whole thing here and say, how do we work this? Remember that it's got to have channels so that the sodium can flow in, and then you got to have channels for the potassium to flow back out, right? So how about if we change the ability of those ions to flow through? In other words, we decrease our permeability. So let me clean this up a little bit. So here's my membrane. I should have sodium out here, right? I'm going to draw 3 in. And I should have potassium in here. So I've got 2 potassiums in here. First thing that has to happen is my sodium channel has to open and sodium's going to flow in. Well, if I decrease the permeability of that so the sodium can never flow in, keep those little channels closed, then you'll never start an impulse. And if that impulse happens to be a pain impulse, you never send that impulse to the brain that says pain, and you say you don't feel it. So these things like anesthesia then will stop the ability or stop the sodium from flowing in, prevents the impulses from actually occurring. So even though you're getting damage to something, so even though there is pain from damage, right, your brain is never getting the message. It never gets that action potential. It never gets that impulse to the brain. So the brain never recognizes that there's pain. So you don't feel it because your brain has to process it, right? If your brain doesn't process something, doesn't matter how well everything worked to that point, if it never processes, then it's like it never happened. Okay. All right. Synaptic transmission. Here's our synapse. And remember, that's this whole into the axon terminal, impulse coming in, calcium channels opening, calcium flowing in, neurotransmitters moving to the surface, and then neurotransmitters dropping across, and then we get electrical signal again. More sodium and potassium basically flowing through. So it's just starting the whole thing over again. So the neurotransmitters are the thing that allows that electrical signal to go from being electrical to chemical and to travel from one cell or one neuron, which is a cell, to the next cell, which might be a neuron, it could be a muscle, it could be something else, but we have to get that message across to the next one if I want to continue like this link to link. So if this is a neuron and this is a neuron, this is a neuron, I have to keep jumping that signal across those synapses to get from like my fingertip, if this is my fingertip, right, to my brain eventually. So I have to keep that going. If anywhere it fails, then it will never get to the brain, I'll never process it. Or from the brain back out to the finger, maybe it's a muscle. So it could go either direction. But anyway, it has to get past those synapses here. So this is a synapse and this is a synapse. And as a reminder, let me clean that up. As a reminder, remember that I talked about presynaptic and postsynaptic. If this is my synapse and my impulse is traveling this direction, then this would be my presynaptic neuron and this would be my postsynaptic for this interaction. But once I get to this synapse, now this one is the pre and this one is the post. So it's just a relational term compared to what part of the synapse they're on. So before this synapse number 1, after synapse number 1, but this is before synapse number 2 and after synapse number 2. All right. So that's where your neurotransmitters like acetylcholine are going to be released. Okay. You have to have the correct receptors on the next neuron if anything is going to happen. It's not going to do me any good to release acetylcholine if there's no receptors on that neuron. That neuron won't respond to it. They're very, very specific. And you might have this really complex interaction of nerves. So I might have one nerve that's coming down and it's actually branching, or something with a little end, and it's coming in contact with several other neurons here. And this neuron might have the right receptors, whereas these two don't have the correct receptors. So it's only going to travel that pathway. These are dead ends. These guys would respond to have different receptors, different neurotransmitters, and so have a different pathway. So it's a way of controlling things, okay? So the effects of these neurotransmitters vary based off of what they're supposed to do on the other side. Are they supposed to relay that message? Are they supposed to kind of slow it down? We might want to slow it down. We might not want, if everybody here, all 3 of these neurons that I drew in have the same, the neurotransmitters, maybe I don't want everybody reacting. Maybe I want some of them to react and some don't. So we do have the ability to kind of regulate the response. Even though an impulse has been sent, what are we going to do with that impulse? Okay. So these are our chemical actions basically that are going to regulate our neurotransmitters and our neurons and what they're doing in here. The first one I'm going to call EPSP. The E stands for excitatory. The P for postsynaptic, that means after the synapse. potential. So here's my neuron. My impulse is coming this way. It's released the little neurotransmitters in the synapse. So there's my synapse, right? And then on the other end is my dendrite. I ran out of room, but dendrite. So this is the axon of the presynaptic. This is the dendrite of the postsynaptic, right? So little receptors on little proteins over here are going to regulate, even though that impulse is maybe very strong in the first one, it's going to regulate what happens on the other end as to whether that signal gets transmitted or not down that next neuron. So an excitatory postsynaptic potential, once those neurons reach these over here, excitatory is going to say, yeah, we want this to happen, and it's going to make this response much more likely to occur. So we're going to have that action potential actually occur. These guys are saying, yes, send it on. It is graded, so it can be yes, 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 send it on, or just yes, send it on. So it does allow for that regulation of how much we're going to send from one to the next one, next one, next one, too. All right, but much more likely to occur. An IPSP is inhibitory. So here's my little axon again. Here's my synapse with my dendrite from the other one, right? And so here's my neurotransmitters being released. So I had this action potential sent. Impulse came down, but the little receptors over here that are picking it up, little proteins and stuff that are over here, are saying, not so much. So even though all of this before has occurred and everything's gone on here, these are saying we don't really need it to go any further. So they're making it less likely to actually send that response down that next neuron. So we're just saying, really don't need that to go any further. Okay. So how it works is it hyperpolarizes that membrane. Remember, so here's that little thing that I had here. So we start out at a lower level. And remember I said if it hyperpolarizes, here's -70, here's -80. If it hyperpolarizes, it's much less likely to reach -55. That's what these guys do. They reduce that right there. And so it's less likely to have enough sodium to flow in to reach that -55 threshold area. So it just kind of fizzles out at that point, and you don't send that message on. Kind of like, back to the nose thing, doesn't really work that way, but think about it with the nose. Less likely to send that message of actually having a smell in the air, right? All right, I can take these EPSBs and these IPSBs, E for excitatory, I for inhibitory, and I can add them together. So I can add more and more EPSBs together in a process called summation and really, really make this likely to send. And you can see in this one, I've got one neuron here and a bunch of axons coming in, and it's really going to send a message along. And it could be opposite. It could be this one neuron going out to many others. But anyway, so the more EPSBs lead to a greater chance you're going to have that action potential actually being sent. More and more IPSPs, more likely it's going to be a dead end. Okay, so it's kind of like, do I want a little signal or a lot of a signal? Little EPSPs, more and more EPSPs. Do I want a signal but not a lot, a little bit of IPSPs, and then we can again make it less and less and less likely to happen so that nothing occurs anywhere along there. So summation. Okay, these guys here, I said that, acetylcholine is the major one that you need to know. Notice it is the first one on the list. Acetylcholine is prevalent in both the central nervous system and the peripheral nervous system. It's responsible for muscle action. That's why we talked about it in the last chapter. So you see it again here in the peripheral. There's the skeletal muscle, right? So in the central, it's going from nerve cell to nerve cell to nerve cell, but then it's going to get to the peripheral and innervate those muscles, okay? It's also important in nerve cell to nerve cell. That's kind of up in there. So it's really important between nerves and nerves to muscles. Then we have a whole bunch of these others, okay? They're all important in their own right, but some of them you may or may not recognize. We're going to come back and talk about norepinephrine at another point in there. So that's one you should know. Norepinephrine, again, is in both central and peripheral nervous system. Notice that it has, the ability to either excite or inhibit. So it just depends on not only what's being released, norepinephrine, which by the way is NE for short, what's being released, but it also depends on the receptors on the cells. So one cell may have receptors that say, hey, respond a lot to norepinephrine and make this excitatory, or some receptors may say, hey, make this inhibitory. It just depends on not only the cell and the chemical, but the receptor that's receiving that chemical. Okay. Dopamine, you probably heard of, again, both in the central and peripheral nervous system. Again, excitatory or inhibitory, depending on those receptors. But this one is this like sense of well-being. This is kind of your happy drug. This is also one, your own personal happy drug that you make, not one that you take from outside. This is also one that is responsible for Parkinson's disease when there's a problem with the production of dopamine and the reception of dopamine. If your cells aren't receiving an appropriate amount of dopamine, that's when you start seeing those Parkinson's types of symptoms. So they're working on that. There's some drugs that kind of simulate it to try and treat Parkinson's. Serotonin, you probably heard about. This has to do with sleepiness. Histamines, you probably heard about. That has to do with, really it has to do with alertness, but it's also, it stimulates so it's excitatory in that case, stimulates your reaction to pathogens. So when you've got something like a bacteria infection or something, it says, hey, immune system, start getting to work, and it hypes it all up. Unfortunately, it also misinterprets some things and makes you feel like something that is not dangerous. Your body thinks it is dangerous, and that leads to something called allergies. So what you do is you take an antihistamine that is against a histamine to stop the histamine reaction so that your eyes stop swelling, your nose stops, being all stuffed up and puffy and all of that kind of stuff. So it's really a normal response. The histamine is a normal response that's supposed to protect you against pathogens. Unfortunately, sometimes it misinterprets things and you get an allergy against something that really isn't or shouldn't be dangerous. Like peanuts should not be dangerous, but it is dangerous to somebody because of your histamine response to it. GABAs, you probably heard about, glutamate, but we're not going to really get into those. But notice, inhibitory, excitatory, they have different reactions. You don't really have to know them, so you don't need to know those. Just pay attention to the fact that some are inhibitory, some are excitatory, some are both. Enkephalins and endorphins we are going to come back to, so that is something you will need to know. Generally, they're inhibitory. These guys bring things down, slow things down. What they do in many cases is they reduce your pain. So they're releasing and they're inhibiting the substance we call substance P, which is down below it. Substance P, think P for pain. That's not really where it is, but P for pain. When substance P is released, it is excitatory, and that is a lot of pain. So it's exciting those nerves, and you're feeling a lot of pain. Enkephalins, endorphins work against that, so they're inhibitory. So they make pain a little easier to deal with, basically. So you release them, and you're feeling a little bit better about it. We're going to talk about this reaction too, by the way, with these two and some exogenous drugs that you take. And then nitric oxide, you may see this, there's a commercial right now that's playing this a lot at this point. But again, that's central and peripheral nervous system. Notice we don't know everything yet. May play a role in memory. We think it does. But it definitely does play a role in vasodilation and transport and stuff. And you see that, that commercial that I keep seeing. It's talking about that. All right. Here is, again, another summary for you. So this is the summary of the neurotransmitter release. So at the end of an axon, when the neurotransmitters, I'm just going to put NT for neurotransmitters, are released into that synapse, and then they're picked up on the other side. There has to be a way to be picked up on the other side. They don't just travel. So there has to be receptors over here. So remember that you have to have the receptors on the other side. Okay, but this talks about the release of these and all the things that are needed in there, including calcium. There's another substance. All of these things are regulated. There's so many things that regulate it. We're kind of hitting the highlights, even with as much as you're learning. There's even more out there. But there's these little substances we call neuropeptides. Peptide tells you that there's a protein component to it. Okay, so it's got a little bit of protein. So neuropeptides have various actions, just like the neurotransmitters do. Some of these actually are neurotransmitters, so they may act as neurotransmitters. Some of them are what we call neuromodulators. So a neuromodulator is something that's going to act on a neurotransmitter and either alter its actions or completely block the action of that neurotransmitter. So that again, where that neurotransmitter is being released into the synapse, it really isn't at that point. So it just stops that whole action of that neurotransmitter. So your impulse, it's a dead end at the end of that one axon. Some examples of those, and I told you we would come back to these. Enkephalin, anything that ends in IN, by the way, you can tell is a protein. So neuropeptide is, protein component. Enkephalins, endorphins, especially the beta endorphins, and substance P. So when you have a lot of pain, we call that painful stress. So during a lot of painful situation, enkephalins are going to be released in increasing amounts. And their job is just to kind of relieve that pain. So bring it down. The reception, everything has to have reception, right? So the reception is actually the same receptor site that morphine uses. This is why we can use morphine as a drug to relieve pain. Morphine would not be any good if it couldn't bind to the cells that it's trying to work on. Well, morphine happens to bind to the same receptors that your own personal drugs that you produce in your body, enkephalins use. And enkephalins, of course, are to reduce pain. So that's what makes morphine such a good pain reliever. But unfortunately, it also makes it, very addictive. Endorphins, your beta endorphins, these are also pain relievers. So they're going to relieve pain, where enkephalins are actually really quick. So, you get a lot of pain really fast. These guys kind of block that, short-lived. Beta endorphins are a little bit longer lived. So they're going to be around a little bit longer and kind of reduce more of a, chronic type of pain versus this would be more of acute. Acute means right here, right now, and a chronic is this ongoing sort of symptom there. So they're both pain relievers and they both have their own function. Substance P is the one that unfortunately we don't want to have. You don't want to. It serves a purpose in your body. You have to have pain in order to quit doing whatever it is you're doing that's damaging your cells and your tissues. So you have to feel pain, but unfortunately it makes us not very comfortable. So substance P is that excitatory neurotransmitter that transmits that pain to your brain and is working opposite of these beta endorphins and these enkephalins that are trying to relieve that pain. So once you increase that pain, you increase that release of substance P, the beta endorphins and the enkephalins are trying to work against that and really to inhibit substance P from doing its job or being released. All right, so opiates. We have two groups that we're going to talk about. I'm not going to say classes because I'm not going to get into the classes of drugs. I'm just going to talk about our two groups as compared to what is natural to your body and what is not natural to your body. If it's natural to your body and you produce it, this is called endogenous. This is something that we would naturally produce and we want to naturally have, okay, because it reduces pain. Exogenous, X means out. So exogenous opiates are these things that we take that will reduce pain, but tend to be highly addictive. And they're only useful because they're using the same receptor sites that an endorphin that your body produces actually has and uses itself. Doesn't have it, uses on other cells. So they all can use those same receptor sites. So that makes them very effective, but unfortunately, they're very addictive. And the reason they're very, very addictive is your body works at balance, right? At this homeostasis. So if I'm producing my endorphins and now I supplement with something like morphine or heroin or whatever it is, then your body says, oh, I have plenty. So it stops producing its own and it kind of ceases the production of the endorphins. And so you now need to have that pain relief. And so you have to take more and more and more because your body's not producing what it normally does. So that becomes that addictive factor right there. Now I'll take it to the point of, okay, I've got to come off this drug and not have this drug anymore, and you stop using that. Now I've taken I've completely eliminated my natural endorphins. I've taken the morphine and I'm addicted to it. Now I completely eliminate that. You have nothing to relieve pain. And what you feel is what we call withdrawals, extreme, excruciating pain, and this need for something to relieve that pain. And that's why it becomes such a problem, is because you can't, without your own endorphins and without the exogenous, your interpretation is a lot of pain because you have not produced your own anymore. And it's going to take a while to get back through that and get to that production again. By the way, same thing's happening with testosterone. So if you're taking, males taking testosterone outside the body, your own testosterone is going to drop. So, I mean, it's one thing if it's already dropped and you need to supplement, but if you're taking it and you can drop that testosterone, then suddenly you can't produce your own. So you're kind of stuck with that needing that testosterone. We all stay at homeostasis. We stay at the right amount. Kind of flip it from one to the other. All right. So processing this, we have these different ways of processing. And I talked about this kind of with, one neuron coming down can branch and affect several other neurons. And that causes, this branching action of actual information from one place to the next. And you can do this. We call this processing. We also call it this pooling, somewhere in there. So neuronal processing is when one neuron, maybe the sensory, is bringing information in, and then it sends it to the next and the next, and then you send out through the motor. All of those in between, these are what we call interneurons. So the spinal cord, the brain, memory, access to all those memories, those thoughts, the behavior that's going to be a result of this sensation, this sensory that's coming in, all of that is part of that neuronal processing. So what's going on in your brain and spinal cord, really? So what kind of function do I need? I have this sensation, this sense coming in. What am I making of that in the interneurons? What am I thinking about it, and what do I want to do about it? That's going to be all that processing. And then you send an impulse out through the motor, okay? And we might have some sort of action, or you might not. So it might excite or it might inhibit. It might be something you completely ignore. So, it just depends on what's going on in that point right there with that interneuron. Okay. Now, we also have these two other terms, convergence versus divergence. I'm not going to draw you a picture because it's on the next page anyway. But convergence means to come together. Divergence or diverge means to go apart. So basically, converge, come to one central area. Diverge, send it out. So we're going this direction, okay, here. So this would be various sensory receptors coming into one place so that you can think about it and deal with it, right? And you may allow for summation in here. Divergent, one central place going out. So maybe your brain telling multiple muscles to do something, okay? The axon branches to many different places. I said I wouldn't draw a picture, and I did. I can't get away with it. All right, pools, neuronal pools. These are just groups of these interneurons that all have to make sense of what's going on in your environment. So they're all kind of working together through little synaptic connections to come up with a general picture of what is happening to you and what information is coming in and how you need to respond to that. So each pool is going to receive input from other neurons, and it's like speaking chemically through back and forth through each other through these synapses. Okay, there's convergence. Better picture than I had. Multiple neurons coming together so that I've got information coming from a couple places headed one direction. So, I mean, kind of think about it like if you had an apple and you took a bite of the apple, you're going to have multiple sensations. You've got the sight. I saw the apple. You've got the smell. You've got that is distinctive to that, and you've got the taste. So you're going to have multiple different inputs coming in from that apple that then goes to your brain, and your brain processes, and that's not as simple as this, but processes all of that. That's an apple, and that's something I recognize through all of these different things. And you could shut your eyes and not see it and still taste it and get the same sort of outcome from that. Yeah, that sound and that taste is that apple, right? But you're bringing multiple sources of input and pulling it to one area. So it allows your central nervous system, your nervous system, to collect a bunch of data, process that data, make sense of that data, and ultimately have some sort of response to that that says, you know, I like that. I'll take another bite of that apple, or I don't like that. That's not my favorite thing, you know, whatever. So you're going to respond to it in some way or another. So it just allows you to make sense of it. So, you know, make it possible for your neuron to sum all this up, put it together, and it's one thing. It's not, you know, a smell, a taste, a sight, and they're all separate. It's all part of that initial, this is the apple. All right, divergence is the opposite. So here's one neuron and it's sending out information to multiple neurons. These neurons send out, and then they may branch too. So you see this one branching, and then, you know, multiple muscle cells or glands or something else that are responding to that. So really what that does is it makes one small response. So this is a, you know, a smaller response. It now becomes bigger and bigger as it travels down, because you're sending it out multiple ways. That we call amplify. So it's making that response bigger. One message, multiple muscle cells that respond to that message, for example. All right. So your impulse and central nervous system, like I said, amplified, gets bigger and bigger because you're sending it out to many different motor units instead of just one muscle cell or one small group of muscle cells. Like the action of maybe your arm muscles or your back muscles that need a lot of strength to move something. They're going to need multiple motor units to be activated, so you need to send that message out to multiple sources or endpoints of that. And that would be it. So we're done with chapter 10. I'll see y'all in chapter 11.